Hello everyone, welcome to GM series of tutorials. In this series, we're going to analyze each or all types of questions that you're going to have in your upcoming final exam. So I hope if you watch carefully all videos and practice yourself a little bit, you will be in a position to get a really high score. The first topic is mathematical induction. So it's very easy. Mathematical induction is used to prove some mathematical expression. So, first I'm gonna give a little theory and then you're gonna see an example. So, in mathematical inductions, there are two steps. The very first step, now, before considering step, let's say that we have a kind of expression P, let's say what, Pn, okay, for example 3n minus 1, and we should prove that this Pn is always a multiple of 2, okay, for n 1 2 3 4 k, etc. So I hope it makes sense, right? So you are given a task to prove that this Pn 3n to the power of n minus 1 is always multiple of 2, 4, and 1, 2, 3, and infinite. Okay, so for this case, you can use mathematical induction. The first step is step number 1. Consider base step. This is called base step. So in this case, you prove that this Pn meets the certain requirement. This requirement is what? That this is multiple of 2 for the initial case. In this case, let's say that I equals to 1. So we have to prove that P1 instead of 1, when we put instead of N1 substituted, we should have the multiple of 2. So 3 to the power of 1 minus 1, this is 2, and of course this is multiple of 2, right? Because it's 2. So yeah, this is step number 1. So step number 2, it's called inductive step. So in inductive step, firstly, assume that the statement that this is multiple of 2, okay, the statement that this multiple of 2 true, that okay, assume that the statement, okay, this is the statement. Let me choose different color. Oh my god, statement. Assume that this statement, okay, the statement true for pk where n equals to k. Okay, so you assume that for k when n equals to k, pk's value is a multiple of 2. Then you do what? Then you prove that, or let's say you prove the statement, okay, for pk plus 1. Okay, so when you prove it, you prove that Pn is always multiple of 2, okay? Always, let's see, always true. So this is very simple. Firstly, base step, you prove the statement for the initial case. Prove for initial case, okay? Then in the second step, inductive step, firstly you assume, this is very important, to assume that pk is true for for n to be equal to k, and then you prove prove the statement for this case. That leads you to proving that our statement, initial statement, that for n Pn is always true, is always multiple of 2 is correct. So now let's solve this example. So Pn equals to 3n minus 1, where n equals to 1, 2, okay, infinite. So let's follow our steps. Step 1. So let's say our I is 1. So let's prove that for initial case the statement is true. So 3 to the power 1 minus 1, 2, and this is true, right? I mean, this is in fact multiple of 2. Now we come to the step number 2. So we assume that n equals to k and pk is true. Okay. Now let's prove. I mean, this is the first case and this is the second. Now let's prove that when n is k plus 1, pk is true. Is true? Let's prove. Let's prove. Okay, let's don't try it. Let's prove. So yeah, so let's substitute pk plus 1 equals to 3k plus 1 minus 1, and as you know, this equals to 3k multiplied to 3, because you know when we have in the power n plus m, you can write it in this fashion: an multiplied to the am. When there's multiplication, you add the powers, right? So let me continue it here. 3k plus 3k multiplied to 3 plus 1. So in this case, now you have to kind of minimize it. You have to not minimize it, but let's say you have to write it in different format. For example, I'm gonna write it like 2 multiply 3k and plus 3k. Okay, so this one, you know, we have here 1, but we don't write it normally. So 2 multiplies 3k plus 3k minus here minus, sorry, here should be minus. So I hope you see the point here. What I mean is that this equals to what? pk, right? So this is true by our assumption, by our initial assumption. See, here we have 2, so this is also true. By true I mean it's a multiple of 2, because there is 2, right? Doesn't matter, 2 multiplied m, it's always multiple of 2. So if this is multiple of 2 and this is multiple of 2, the sum output is also multiple of 2. So that means our output is the value of pk plus 1. If pk plus 1 is now true, that means we proved that for n with these values, Pn is always multiple of 2. Okay? This is so simple. I hope you got the idea. The very first step, proof for initial case 1, then assume that for k the statement is true, and then prove this statement for k plus 1. If you prove it, then you prove that it's also true for the given n value. So I hope it was understandable for you. See you soon in our next tutorials.